Solving problems with dynamic programming. So today's problem is rod cutting problem. A company buys a long steel rod and cuts them into shorter rods before they sell. We assume that each cut is free. Let the price of the rod of length I is P of I. So, given a rod of length n inches and the table of prices Pi for I equal to 1 to n, the company wants to know the optimal way to break a rod of certain length n so that the total price of all the pieces is optimal among all the possible prices. There will be only one optimal value, but there might be many optimum values. I mean, optimum values can be more than one. Our goal is to determine one such optimal solution, that is R of n, to this problem with optimum value, that is maximum value in this case. If the price of the rod is large enough, an optimum solution may require no cutting at all. So the general approach of dynamic programming. The four steps that we need to follow are: we have to first characterize the structure of an optimal solution. These steps involve finding the optimal structure of the problem. Then recursively define the value of the optimal solution. Finally, compute the value of an optimum solution, typically in a bottom-up fashion. We can then construct an optimal solution from the computed information. Steps 1 to 3, these are the steps 1 to 3 are the basic steps of dynamic programming. Step 4 is needed. What we need is needed when we need the optimum solution and not just the optimal value. Analysis of rod cutting problem. Say you are given a rod of length 4. So there are different ways you can cut it. You can cut it in 4 like this. This can be one way. Of each of length 1 you can cut it at 4 steps, or you can cut it in 2 parts. One is of length 1 and other is the length 3. So there can be several ways. So since it is 4, so there are 8 different ways in which you can cut the rod. So the aim of the company is to find how many possible cuts gives a optimal value of revenue, so that they can get the maximum revenue by cutting the rod in how many pieces. Let us denote a decomposition into pieces using ordinary additive notion. For example, a rod of length 7 can be cut into 2 rods of length 2 and one of length 3. If optimum solution cuts the rod in k pieces for some, then the optimal decomposition n is given by I1 plus I2 till Ik on the rod into pieces of length I1, I2 till Ik, provides the maximum corresponding revenue. So the rod is of length n and you are cutting the rod into this many pieces. This is of length I1, this is of length I2 till Ik, and this cut is producing the optimum or the maximum revenue in this case, and revenue will be the price of this piece plus price of this piece plus price of this piece, that is P of I1 plus P of I2 plus till P of Ik. So for a sample problem, the optimal revenue figures Ri for I equal to 1 to 10 with the corresponding optimum decompositions are shown. That is, for revenue for 1 will be for P, length 1 will be 1, for 2 length 2 will be 5, for length 10 will be 30, and so on. That is, if you divide a rod of length say 4 into 2 rods of length 2 inches, so then 2 is 5, so for each 2 rods you will get 5 plus 5, that is your revenue will be 10. So this is the table. Solution to rod cutting problem. So cut rod is the procedure that helps us find the maximum revenue possible for a rod of length n given P. P is the price table and n is the length of the rod. This is the price table. See, for the length 1 you will get a revenue 1. For length 2 you will get a revenue 5. Length 3 you will get a revenue 8, and so on. So if length is 0, then we will return 0, else we will initialize this q with minus of infinity. Now for every possible length from I equal to 1 to n, what we do? We find the max of q, that is the present price, plus p of I, that is the price table. We'll call the, for this length we will call the price table, plus cut rod p and n minus I. So this is calling of this procedure, and we will return q. So can we improve it? We need to somehow make it possible to get the solution by solving each subproblem only once. The main trick we can employ is to store the solution to a subproblem after it is evaluated. Use it whenever it is required later in the process. And this we do by applying dynamic programming. This method might take more space, but sometimes converts an exponential time solution to a polynomial time solution. So as you can see, this algorithm was exponentially increasing in time. So we can convert this exponential time solution to a polynomial time solution using dynamic programming, provided the number of distinct subproblem involved is also polynomial in the input size. So this kind of a solution is time memory trade-off. Dynamic programming solution to rod cutting problem. We call this memoized cut rod. It is the price and this is the length. So we will initialize an array R of length 0 to n, and for every value we will initialize R of I equal to minus of infinity. And then we will call memoized cut rod aux for this p value of n and the value of R. So what the memoized cut rod aux does? If R of n is greater than 0, it will obviously return R of n. If n is equal to 0, then q will be 0. Else q equal to minus of infinity. Then within this else, for each length of the rod cut, we call a max on q present plus p of I plus memoized cut rod aux. This is an recursive function on price p of n minus I and R. Then Rn is equal to q, and we will return this to memoized cut rod. Analysis of dynamic programming solution. So the running time of this algorithm can be written as t of n, that is equal to 1 plus t of j's summation from 0 to n minus 1, that is the length of the rod. So this is a recursive solution whose t of n will be in order of exponential, that is it is 2 of n.